Every single time you load a web page, send a message, or stream a video, you are relying on a protocol that was designed more than 40 years ago. It's called TCP. And honestly, it's the unsung hero that stops the entire internet from just falling apart. So today, we're going to pull back the curtain and see how this digital workhorse actually gets the job done.
All right, let's start with an idea that sounds completely backwards. What if the internet, the one you're on right this second, was intentionally designed to be unreliable? To just drop your data?
Well, believe it or not, it kind of was. See, the network layer underneath everything, the Internet Protocol or IP, it works on what's called a best effort basis. And that means it makes absolutely no guarantees. It'll try its best to get your data where it needs to go, sure, but it doesn't promise it will get there safely or in the right order or even that it'll get there at all.
So you end up with this totally chaotic environment. All your data, your emails, your photos, gets chopped up into these little pieces called packets. And as these packets zip across the globe, they can get dropped by busy routers, they can take different paths and show up completely out of order, or they can even get duplicated along the way. It's really like a postal service that sometimes just loses your mail, shuffles the pages of your letters, and then delivers the same junk mail to you twice. So if the very foundation of the internet is that messy, how in the world does a multi-gigabyte file download perfectly? Or how does a web page load with every image and piece of text right where it's supposed to be? Well, this is where the hero of our story comes in, a protocol called TCP. TCP, or the Transmission Control Protocol, is basically a layer of trust that we build right on top of that unreliable IP layer. Most of its logic is running deep inside your computer's operating system, in the kernel, and its entire job is to create a predictable, reliable connection out of all that chaos. And to do that, TCP makes 5 core promises. First up, reliability. If a packet gets lost, TCP makes sure it gets sent again. Simple as that. Second, ordering. It takes all those jumbled packets and reassembles them in the correct sequence. Third, flow control. This is what keeps a super fast server from completely flooding a slower device like your phone. Fourth, and this one is absolutely crucial, congestion control. This stops the entire internet from grinding to a halt under its own traffic. And finally, multiplexing, which is the magic that lets your web browser, your music app, and your email client all share one internet connection at the exact same time. So, how does this whole process even kick off? Before a single byte of actual data is exchanged, 2 computers have to formally introduce themselves. They have to get in sync using this very specific digital ritual. It's what we call the 3-way handshake. So first, your computer sends out a SYN, or synchronize packet. It's basically saying, hey, let's talk. Here's my starting number. The server then replies with a SYN-ACK packet, which means, okay, I hear you, and here's my starting number. Finally, your computer sends one last ACK packet back that says, got it, we're in sync, let's go. And only then is the connection actually ready for data. But here's the catch. This handshake, as essential as it is, has a cost. Time. It adds a full round-trip delay across the network before any real data can even begin to flow. And that little bit of latency is precisely why reusing existing connections is one of the most important tricks for making the web feel fast. Every brand new connection has to pay this time penalty, which is also why clever new things like TCP Fast Open were invented, just to speed this part up. Okay, so the connection is open. How does TCP manage to send data without being painfully slow? I mean, it can't just send one tiny packet and then sit there waiting for a reply, right? Instead, it uses this absolutely brilliant mechanism to send a whole flood of data efficiently. It's called the sliding window protocol. This lets the sender fire off an entire window of packets all at once without needing to wait for a separate confirmation for every single one. This is what separates a slow crawl from a lightning-fast download, and it's really what makes high-speed data transfer possible today. Now, the speed of TCP is constantly being negotiated between 2 different windows. On one side, you have the receiver window. Think of this as the receiver, like your laptop, shouting, hey, I've only got this much memory buffer free, so don't send me more than that at once or you'll overwhelm me. But on the other side, you have the congestion window. This is the sender's best guess for how much data the network itself can handle without getting clogged up. And the actual amount of data TCP is allowed to send is the minimum of those 2 values. It's this beautiful dynamic balance between what the receiver can handle and what the network can handle. So how does the sender know what's gotten through? Through acknowledgements, or ACKs. Back in the day, it was pretty simple. The receiver would just say, I got everything up to packet 100. But modern TCP is way smarter. It uses something called selective acknowledgement, or SAC. This lets the receiver report the exact gaps in the data stream it received. That way, the sender only has to retransmit the precise packets that went missing, which makes recovering from errors incredibly efficient.
And that brings us to what is probably TCP's most important and sophisticated job, preventing the entire internet from collapsing under its own weight. And I'm not being dramatic here. This isn't just a theoretical problem. It actually happened. Back in the late 1980s, the early internet suffered from something called congestion collapse. As the networks got busier, packets started getting dropped. In response, computers would just aggressively resend all that data, which of course only added more traffic to the network, which caused even more packets to get dropped. It was this vicious feedback loop that literally ground the network to a halt. TCP's congestion control was invented to solve this exact crisis.
So to avoid that ever happening again, TCP performs this really careful dance. It starts off in a phase called slow start, where it exponentially ramps up its sending speed to quickly figure out how much bandwidth is available. But the very moment it detects a lost packet, the first sign of trouble, it slams on the brakes and switches over to congestion avoidance. From then on, it grows its speed much more slowly and cautiously. It's this constant cycle of probing for more speed and then backing off when it senses danger.
Now, here's a really important thing to understand. TCP isn't just one single unchanging algorithm. That whole congestion dance I mentioned is actually modular, and it's constantly evolving. Your phone, your laptop, they're running much more advanced versions today. For instance, an algorithm called Cubic is designed to be more aggressive on modern high-speed networks. Meanwhile, Google's BBR algorithm tries to build a sophisticated model of the network's capacity instead of just reacting to lost packets. And this just perfectly illustrates how deep this rabbit hole goes. Trying to optimize TCP is a never-ending challenge. You have this delicate balance between what an application needs, what the network can actually handle, and all the dozens of little settings in each of these algorithms. It makes this a field of constant cutting-edge research. What's just so incredible when you think about it is that this protocol, something conceived decades ago, is still the absolute bedrock of our digital world. It's a real testament to a design that was built from the ground up to bring order to chaos, a design that's constantly adapting through this delicate dance between speed and stability. The real question for the future is, as our demands for data and for speed just continue to explode, how is that dance going to have to change next?